Hi, my name is Evan Lobiser. I'm a student in electrical engineering, and I've been studying and doing research in this field for about 8 years now. I'd like to tell you about a class I'm teaching called Exploring Nanotechnology, what nanotechnology is, how we make nanotechnology, and what it can be used for. The class is called Science of the Small. I'd like to tell you more about it. So first off, when I say the word nanotechnology, what comes to mind? What do you think nanotechnology is? I like to define nanotechnology as processes that can control matter on an atomic or molecular scale, or structures that are about the size of atoms and molecules. This is a pretty broad definition, and so nanotechnology has a wide range of applications in fields like medicine, where it can improve drug delivery and diagnostics, in electronics, where we can build better and faster transistors, and in optics, where we can make better computer displays and televisions, for example. It's a really new field, and it's pushing the limits of what we know in physics and science and engineering. In this class, we're going to learn about structures like these, carbon nanotubes, basically a single sheet of carbon atoms that's rolled up, and we'll learn about how their unique electrical properties and strength properties allow them to be used in a variety of applications, including things like space elevators or really high-tech, very small electronics. Here's an example of something I work on in my research, which is a very high-frequency transistor. Again, a switch that, a transistor is like a switch or basic building block of a computer processor. And we use nanotechnology to improve these and make them faster by making them very small. So what else can nanotechnology do? The applications are really almost limitless. We can, like I said before, we can make better transistors or switches in your computers. We can make brighter TVs and displays, and you may have already seen some screens like this. There's improved cosmetics, basically fancier sunscreens and mascaras that use nanoparticles to make them work better. And there's lots of research going on in better medicine and hopefully things even like tiny robots that can build other small structures, and even quantum computers, which could revolutionize technology as we know it. So when I talk about nanotechnology, how small is it? What is a nanometer? How big do you think that is? So just for comparison, in 1 meter, or about 3 feet, there's 1 billion nanometers. For reference, a human hair at the tip is about 75,000 nanometers wide, and in just 1 second, the hair grows 5 nanometers. The wavelength of visible light ranges from 400 nanometers to 700 nanometers. And so some of the structures we'll be looking at are smaller than this visible light. For example, this pneumonia bacteria here, one of the smallest living organisms, this image was taken with an electron microscope because it's too small to even be seen with visible light. And we'll learn how all these technologies work in this class. So for comparison to those natural objects, here's a few more man-made structures at the nanoscale. This is a cutting-edge transistor made by IBM, and companies like IBM, like Intel or AMD, all the electronics they make for computers and graphics cards and all that stuff, they make it better each year by making their transistors smaller and smaller. By doing that, electrons can move from one side of the transistor, this dark rectangle here, to the other even faster, and they can fit more of these transistors in a given area to make the chip even better. Another example of tiny nanostructures are called quantum dots, where scientists can assemble them from as few as 100 atoms and use their unique properties of quantum mechanics to do things like improve LEDs and lighting. And these structures, because they're made of only just a few hundred atoms, can be as small as 10 nanometers in dimension. So how do we learn to think about the nanoscale? This is something I do in my research a lot, and something we'll learn to do in this class. Because it's so small, there's a lot of different rules than we see in our everyday life. For example, surfaces and interfaces between materials become much more important than the things that happen inside the material. For example, think about a balloon that's blown up. When it's full of air, the air makes up a large proportion of the balloon. The surface is just a thin outer shell. But if you deflate the balloon, all the air leaves, and all that's left is that outer shell, or the rubber part of the balloon. That surface of the balloon becomes much more important as the balloon gets smaller. And the same thing happens with nanostructures. Another thing, gravity is negligible at the nanoscale because the objects weigh so little, the force of gravity doesn't affect them much compared to things like electric charge or the forces like geckos use to climb glass. We'll learn about those forces and how the same thing that geckos are using to climb a smooth surface will move nanoparticles around. We'll also learn about scaling laws, or how to make things smaller in a certain way. And again, this is something I do in my research a lot. I study transistors and find what aspects of them we need to shrink, what aspects of them we need to improve to make transistors better. For an example of scaling and how to tell what's important is an ant. We all think of ants as very strong, able to lift many times their own weight. But I'd like you to imagine what would happen if you were to increase an ant in size by a factor of 10 in all directions, length, width, and height. So first, let's look at the legs of the ant. If we were to increase those by a factor of 10, they would basically get 10 times longer, but they'd still be a long, skinny, basically one-dimensional line. So they'd be able to hold about 10 times as much weight as they could at the original size. Whereas what would happen to the body is it would grow in 10 times both in length, width, and in depth, and so it would have a volume about 1,000 times larger than the original ant, and would weigh about 1,000 times more. So that leaves us with a leg that's 10 times stronger, holding a weight that's 1,000 times more. So scaling an ant up in size would not make it very strong at all. It wouldn't even be able to support its own weight. These kind of things happen in nanotechnology as well, and we'll learn about how to scale things and make them work efficiently and do things that wouldn't be possible with devices the size of things in our everyday life. So finally, how are these things made? Here at UCSB, we're fortunate to have a very good fabrication facility. And in this class, we'll take tours of this lab, as well as some other labs for growing semiconductors and other metals. And we'll learn exactly how scientists are making devices. For example, here we have people working in a clean room to deposit metals. And they're wearing these suits, maybe not for the reason you would think. It's not to protect themselves from the chemicals they're using as much as it is to protect their samples from themselves. Even if you've taken a shower today, human beings just aren't clean enough to make these structures without protecting them from shedding skin cells and hairs and stuff like that. We'll also learn tools for doing depositions like here, or how to make etches and etch structures like this one shown here, and also how to make tiny patterns at hundreds of nanometers in size using tools like the electron beam writer we see here. So in conclusion, nanotechnology has a vast possibility for innovation. There's a lot of cutting-edge technology to be explored, and the possibilities of what we can do with it are just being discovered. I'd like to invite you guys to come and learn about this with me, and I hope you'll think about taking this class. Thank you.